Okay, hey, thanks for the invitation. So I'd like to tell you about joint work with Oded and Barak Weiss. Or is from Hebrew University, Barak is from Tel Aviv. So it's about a question goes back to a classical work of Minkowski about covering space. So you must have heard about similar questions. Let me show you maybe an animation just to set the stage so you know what I'm talking about. So one of the even better, like one better known problems is that of packing. So imagine I have a sphere or balls and I want to pack them in space. So I want to have cover as much as possible with have the biggest possible spheres such that they don't intersect. So you can imagine I can make this ball bigger and bigger. And at some point, I have to stop, or that's the packing radius of this ball. So this is the setup we'll typically have, right? So I have some convex body. In this case, it's a ball. It doesn't have to be a ball; it can be any convex body. And typically in high dimensions, I care about high dimensional case. And the packing question asks, given a convex body, what's the best way to pack it? In the sense that you want to have as much of space covered. In this case, it's not a very good packing. I don't know, it's maybe like, 25, 30%. Of course, better packings for spheres. The question we care about is the lesser known sibling of packing. It's covering. So what I want to do, it's also a classical question. I want really to cover all space. So let me go on, and you see what's happening now is that I have some points covered twice, like here. This is 1, this is 0. Okay, and as I go on, I slowly have more and more of the space covered. And let's see if I can catch that exact moment. I guess here. So this moment here, no point is covered 0 times, right? So you have some points like here covered once, and some points here covered twice. At that point, we have covering of space. And we can ask the same question, like what's the best density or the smallest density of covering space by balls that one can achieve. So when I talk about packing, density is just the volume of the ball divided by kind of the co-volume of that lattice, or kind of how much space each point in the lattice takes. In this case, it's the same thing basically. I divide the volume of that ball by the co-volume of the lattice, or how much space each point takes. So this I'll define it in a minute. This is the covering problem. Let me mention just a few more comments. Again, it doesn't have to be Euclidean ball. It's typically in high dimensions. The low dimensional cases are very interesting. There's been lots of progress in recent years. You probably heard Vyazovska's breakthroughs about packing in 8 dimensions, 24 dimensions. There, the challenge was actually to bound all possible packings, not just lattice packings like here. I'll mention that also, in this case, it's a lattice. It doesn't have to be a lattice. So one more comment I want to mention about this is that everything here is kind of like dilation and scale invariant. If I replace the lattice by like 2 times the lattice, like dilate by a factor of 2, nothing changes. It's really kind of a question about the convex body versus the lattice. Okay, so let me go back to maybe a few definitions. I'll try to do it here because I'll need the projector. So covering. Then do stop me, ask any questions, because I'll try to minimize definitions, and maybe I cut too many definitions. It's the first time I give this talk. I should also say this is based on 2 papers. One of them appeared in JAMS last year, and the other one is still in progress. Should hopefully be posted very soon. So again, what is covering? So I have some lattice L in Rn. It doesn't have to be a lattice, just a discrete set in general. Typically, we'll work with lattices. I'll define it in a minute. I have some convex body K, and convex bounded, so it's convex and bounded body. So it's and we say that K, L is covering if simply L plus K is all of Rn. This is covering. This is like a Minkowski sum. Now, typically, we'll care about lattice coverings. So what is a lattice? A lattice is simply the set of all integer combinations of some n linearly independent vectors. So AI. Okay. This is for BI being B1 up to Bn being linearly independent in Rn. Linearly independent. Okay. So one invariance that we often use is that covolume I mentioned before. It's basically the kind of gives you some scale of the lattice, is the amount of volume each lattice point has. And you can define it, if you wish, as the absolute value of determinant of B. B being that matrix, the basis matrix, consisting of the elements of the vectors B1 up to Bn. Okay. And just because everything is kind of scale invariant, we will typically just assume that the lattice has determinant 1. This is without loss of generality. So, almost all lattices I'll have here, let's call it Ln. It's just lattices of covolume 1. Okay, so covolume sometimes is called determinant. Again, it's just scaling, just to keep everything scaled. And then the critical parameter we want to consider is that of covering density, right? So basically, kind of what's the average number of times the point is covered. So this is covering density. It's really what we're trying to minimize, right? Covering density. Yeah, as I was saying, it's kind of the lesser known sibling of covering of packing density, which has seen lots of interest in recent years. So basically, I want to ask, so if I give you some convex body, think of it as being just Euclidean ball for simplicity, and I give you some lattice L. It doesn't have to be a lattice, but basically what I want to look at is that ratio of the volume of that dilation of the body, so that it's covering by the covolume of L. Okay, this is over all R such that L plus RK, or all dilates that are covering. Okay, so again, so if I give you a convex body and give you some lattice, you can see like how should I scale the convex body so that everything is covered, and then you can look at the density. So this number here, this ratio of volume to covolume, you can think of it as really just the average number of points, average number of times a point is covered. Okay, the best is 1. This is what you get. They have cubes. If I get cubes, right? So I just tile the space. This would be just 1 because the volume equals to the covolume. Okay.
So since you put R there, is the volume of K also 1?
The volume of K, actually, this is independent of the volume of K because I'm allowing you to dilate K in any way here. Maybe I didn't get the question.
If you're allowed to dilate, then you want the volume of K or the volume of R?
I want the volume of RK.
Oh, sorry.
Yeah.
Okay, good.
So because K is, I still don't care about the scale of K. I try to scale it to fit to cover the space, given that L. And the only other definition I need for now is basically the best way to cover space, given a convex body. So I tell you, in the convex body, what's the best way to cover space? What is the best lattice covering of space with that convex body? So this is infimum over all, without also generality, covolume 1 lattices. Okay. So this is it's a good time for questions. This is basically all I need to start talking about known work. And is that okay? So what was known, again, I was saying, is a classical question. Most of the work was done by Rogers in the 1950s. He did Rogers, I think some of his students also. So what was previously known about these questions? So if you know a bit about packing, the surprising thing is things are so much tighter here. Things are so much, the bounds are so much tighter here. In packing, there's a huge gap between what the best known packing, and at least asymptotically within the best known packing and the best bounds we have. And here it's actually surprisingly tight. And if you think of, for simplicity, as the ball, or if you look at the ball, the special case of the ball is actually very well understood. This is work of Rogers from '59. So Rogers showed that there's actually an amazingly efficient way to cover space using balls. It's kind of counterintuitive. So it's showing you that theta k is n times some polylog, which I think he cared about all the constants, but for us it's simply n times polylog n. And it's kind of remarkable. Now, keep in mind, this is not radius, right? So this is volume. So it means that if you think like you clearly need a ball of volume 1 to cover space, if the lattice has co-volume 1. This is saying the volume is just a tiny bit more. The volume is like n times more, or n polylog n more. In terms of radius, this means you just dilate by like 1 plus log n over n. So just tiny dilation, the volume is just a tiny bit more than that of a volume of a ball of volume 1, and you already managed to cover space with balls. So this is very tight, especially if you contrast this with what's known about packing. It's kind of a remarkably tight bound. Also a lower bound of C times n, so it's kind of in the right ballpark. So the lower bound is Coxeter, Few, Rogers. This is Coxeter, Few, and Rogers in 59, and this is here. This is Rogers in 59. Okay. So this is again. This is just for the special case of the Euclidean ball. So this is the L2 ball. And Rogers uses some of the properties of that convex body, and it's not so clear how to extend this immediately. But he has also result for general bodies. So generally, this is the question we mostly care about. So generally, if you have any convex body, it doesn't have to be the Euclidean ball, it can be anything. Rogers was able to show another result that it's at most or less than n to the log base 2 log n plus c. Okay, so this is worse. This is not polynomial. It's slightly super polynomial, and that's been the best bound for many years. Again, the same paper, I think. He had many papers during those years. I think it's the same paper.
These upper bounds are lattice packing.
Say again?
These upper bounds are lattice packing.
So this is all lattice covering, and let me mention now. Let me mention now what's known generally. If you when you don't care about lattice coverings, things become much easier. Basically, you kind of take some random shifts or something, and maybe I'll mention it later. But for just as a comment, so for non-lattice, if you don't care about lattice coverings, it's known. It's actually an earlier paper of his where he was able to get denoted by maybe theta k prime. So you don't really care about it being a lattice. It's basically what he does is like some random causes of a lattice. It's not that far from a lattice, but it's not a lattice. He gets n log n, and even gets all the lower order terms. It's like n log n, and even gets a constant 4 here. It's actually a later paper with Erdős. So this is again the same. This is the paper, same author but different years. I think it's a separate paper. Rogers 57. But again, so this is the non-lattice case. Again, super. I think the lower bound still holds. It's still C times n, so it's super tight between Cn and log n. But the question we want to address here is what happens in the lattice case. Can we have good lattice coverings of space? Right? And generally for any convex body, like for a ball, it's already known. Can we do it also for arbitrary convex bodies? Right? It seems like natural question, and this is the first result that we proved. So this is with Oded Regev and Barak Weiss. This was last year, and we basically show this is for all convex bodies. So for all k convex, that is less than C times n squared. Okay, so previously it was quasi-polynomial. It was n to the log n, and we show it just n squared. So you can any convex body, you can cover space using a lattice. You have a lattice covering where the kind of average number of times that a point is covered, or the density is n squared. Okay, we don't have a matching lower bound. It could be the right answer is n. We don't know yet. But this is the best known so far. It's an improvement on the n to the power log n that Rogers had. Okay, so questions about main results.
Possible to describe what the construction looks like for these good lattice coverings? Is it just sort of random lattice?
Okay, great. So this is what we actually prove is a stronger result. It also gives you some information about how we achieve those coverings. And that's exactly as you're saying. What we actually do is simply take a random lattice, right? That's how we like choosing good objects. We just choose them randomly. and it's exactly what we do. So let me, and this would imply theorem 1. So it's a stronger theorem. So again, the same setup. So for all k convex, there exists, and actually for all some n, it's most n, we show that the probability, if you choose a random lattice, I mentioned in the method, what is that exactly? What is the random lattice? Bear with me. So the probability that is covering is bad. It's bigger than n times n squared. That's decays very quickly with the m. So it's like, and whenever I write a c, it's some number I don't care about. It could be different from one place to the other. Some constants, some absolute constants. So this is the main theorem we actually prove. So let me explain a bit what's going on here. So this is something we call the Dhar-Ziegel distribution, but this is a very natural, or the most natural, I think, a probability, uniform, in some sense, probability distribution over lattices. The theory was developed by Ziegel, and I won't go into definition. I mentioned some properties of it, but it's really the nice thing is kind of like a hard measure. It's invariant under linear transformation. So if you choose a random lattice, do many things like you just do some linear transformation to it, the result is still, as long as the determinant is 1, the result is still a random lattice. So it's a kind of the right measure you want to work with. It's very natural. It has lots of nice properties. The details don't really matter for us. I will not bother defining it formally, but it's not difficult to define. You inherit it from the Dhar measure on SLNR. So you don't have to know much about this, except that some way of choosing a random lattice is very nicely defined. There's lots of nice properties. What we're showing here is that the probability of being somewhat bigger than n squared decays very fast. So in particular, it implies theorem 1. Just take this m to be big enough constant, like 100 or something. This will give you something less than 1. So it shows you in particular there must exist a lattice, because the probability of a random lattice being good or being bad is less than 1, so there must exist a lattice that has good covering density. So let me just write it down. So corollaries. So the first one is that there exists some constants, big C, again, it's a different constant each time. So the probability that a random lattice has covering radius greater than C times n squared, this is less than 1. And as a result, you get theorem 1. So basically we show, you choose a random lattice, it's going to be a good covering. And that's, we also show some tail behavior. So the nice thing about theorem 2 is it really shows you some tail behavior, shows it also decays fast. So let me state that next. So the probability of this beta k of L being, say, bigger than, just an example, being bigger than some n cube, this is less than something exponentially small in dimension. So it's exceedingly unlikely that you get a paired lattice that is has covering density bigger than some constant times n cubed. Just to give some comparison, the previously best result is by Stoenbergson. And he showed, I think he had something like 1.76 to the power n here instead of n cubed. So it was a much weaker result. This was Stoenbergson in 2012. Okay. One thing I should mention is like
for the Euclidean model, it is n in your theorem, or
no, actually I don't know. We don't use anything. We don't know how to use any properties of the Euclidean ball. Maybe it's worth.
Really, so really.
I mean, for Euclidean ball, there's also
n log n to the power, right? Sorry, what Rogers proved. N times log n to some universal.
So for Euclidean ball, we know based on Rogers that there is a way to get covering density very close to n. It doesn't really use a random lattice. That's the issue. So all those proofs, like they feel like they kind of random. So maybe it's enough. Maybe you can actually show that the same happens for random. We didn't try. Maybe the same happens for random lattice. I would bet so, but somehow, yeah, they need some. Yeah, they use some things that don't immediately translate. But it's a good question. Like I would bet that for a Euclidean ball, you should get really like n or n log n, something like n log n. Just as a side remark, I mean, you might be wondering, why do I start with tail bounds? Why not I just give you, like, the first thing you ask is like, what's the expectation? It shows the expectation is good and I'm happy, right? It shows that like a typical lattice expectation is n squared. It turns out that's actually not true. Actually, the expectation is infinite, and that's kind of surprising. That's a property of the space. I mean, there are all those like corners of the space of lattices where you get basically you get very short vectors in your lattice, and that kind of ruins everything. So, and they happen with very small probability, but it's enough to ruin the expectations. Anyway, it's not.
So you're really not assuming any isotopicity or something. So because if you have very, very long and narrow body, you still take a random lattice.
And that's a nice thing about the distribution of lattices, because it doesn't actually matter if your body is like this very long needle. It doesn't really matter because the distribution of random lattices, it's invariant under any linear transformation. So if you wish, you can assume, but it's without autogenerality. You can assume that the body is in any nice position to not affect anything. It's counterintuitive, but yeah. So it's a nice distribution that doesn't really care about this. Okay, so this is very quickly again. I'm running very fast. It's the first time I give the talk, so maybe I'm not calibrated right. Do interrupt me with more questions. This was kind of the work we did last year, and I want to show you what the second paper is about. So again, the first paper was about covering. You just want to cover all space and do it in the most efficient way, right? I don't want very big bodies. What we did next is basically we kind of continue that video further. So let's try to think what happens if you go further on, right? So at some point those balls keep increasing in size. Right. And you see, like, for instance, at this point here, or the no point is covered once. I think all points are covered at least twice. And I keep on going and going. So this here and then bigger and bigger and bigger and bigger. And at some point, like say here, I don't know, you start seeing that any point in space is covered, I don't know, I lost track, but maybe it's covered like between 7 and 9 times, which is what we call like smooth covering. At this point, like covering was basically saying it's at least one everywhere. Right? Everywhere you must get at least one like ball above you. Here, I want to make sure that no matter where you are, the number of balls above you has to be within, say, 10% of the same number. So kind of should be L infinity, some uniform smoothness of this function. Okay, so this is what we call smooth covering. Let me show the whole movie kind of from the beginning. So again, we're packing, and now we're in the covering range. At some point, depending on this epsilon, this 1% I'm willing to tolerate, I'm getting to this what I would call smooth covering. It's not like everyone is exactly the same, of course. There are always, some fluctuations because of the boundary of the ball, but it's maybe 1%, 10% away from each other. So, why do we care? So let me ask why do we care? So this is smooth covering. That's kind of the paper that's still under, it's still in progress. So actually this problem is showing up in some of the early works. So there was, I think Rogers cared about this, and I think it's kind of implicit or shows up in work of that Rogers did with Erdős in 62. So implicit in Erdős and Rogers, and they didn't quite look at exactly this, but it's kind of the question they were asking. They want to make sure there's not too many balls covering any point. What they really did, if you want to know the result, is really the non-lattice case. So either they could not or did not care about the lattice case. I assume they cared, but they could prove the non-lattice case, which is of course much better understood. And they basically showed something like that. So they showed that for the non-lattice case, for any convex body, you can get density of n log n, or some constant n log n. So some constant n log n, what I would call like smooth covering density.
The non-lattice case is easier because you just take random shifts and it's like expectations.
You have lots, yes, you have much more randomness to work with. So you take random shifts, yeah. And then it's basically straightforward analysis. I'm slightly simplifying. There are some issues. It's not that straightforward, but yeah. So smooth covering. Of course, there's some dependence on this epsilon, like how much you're willing for the smooth to deviate from really being flat. I mean, but I'm not showing it here.
What the statement means here is that you can rescale the body so that every point is between one constant times n log n and another constant.
Exactly. So yeah, so you can rescale the body, right? So that we know that on average, the number of times the point is covered is always the density by definition. So because the volume of the body is n log n, and the volume of the co-volume of the lattice is 1. So kind of on average, I get the expectation is exactly C n log n. And what it's telling me is that no matter where you look, right, you'll have either this like plus 1% or minus 1%. This narrow window around C n log n exactly. So this is, let me define it next. I was planning to define it. So and again, this is implicit in the work. We also have a proof of this. There are multiple ways of proving it. It's not, this is the non-lattice case is as Zev was saying, it's possible to prove. So let me maybe just to define it formally, maybe I need a couple more definitions. So this is just the number of times the point is covered. So this is the number of lattice points in L, such that the point is below the ball centered at, or that's the convex body centered at the lattice point. So this is for any given point X. It tells you, we have like 10 of those bodies above me, 20 and so on. And as I was saying, let me just again point out, I've been saying this multiple times, but let me write it out finally. Anyway, the expectation if I take a random X in space or in a torus, whatever, a typical point, the average would be volume of K divided by the co-volume of L. Okay, this is just by like Fubini or something. This should be hopefully intuitively clear, just the volume of the ball divided by the co-volume of. So maybe give it a name, it's N K. That's like the average, what you expect to be given the volume. And we want to be close everywhere. So what we want is this. So this is the smoothness of the covering. So let's call it eta KL. That's the max over all X in space of NKLX divided by NKL minus 1. Okay. This is the expectation. And we want to be, say, always within like 1 plus minus epsilon of the expectation. That's we say. Okay, so if just notice, like you just see the connection, if eta KL is less than 1, then it's covering, right? And in particular, it's covering. So this is clearly the stronger notion. I mean, if it's less than 1, it means you can never really touch 0. This number can never be 0 because otherwise this will become 1. So eta KL being 1, meaning that always between 0 and 2 times the average. But if it's less than 1, it's in particular it's covering. But it's more than that. I have to be always close to that average everywhere.
So up till now, all notions exist in a discrete case, like in coding theory. Codes are packing and covering codes are covering. And did anybody consider smooth covering in this case?
So this is exactly the way you prove it. So maybe let me get to the proof. But I think the answer is so I mean there are many ways of maybe several ways of interpreting the equation, but I think you're basically hinting at what we'll do in a minute. So basically, okay, let me say it already. Let me first state the theorem, and then we can talk about how we prove it. So this is the eta, just kind of how much we deviate from being truly uniform. And what the parameter we care about is this. It's called psi KL epsilon, and this is just the infimum of again, just like before. It's like the density, the volume of RK divided by the co-vol of the lattice, which is typically 1. So the denominator is typically 1. And what we want to make sure, instead of saying covering, we want to make sure it's like smooth covering. We want to make sure that this eta KL is less than epsilon. So say some 1%. You don't have to worry about this epsilon. Maybe it's just 1%. Say again?
You want 8 of RK, KL.
Oh, I do want that. Thank you. Thank you. Okay. Exactly. So I want RK to be smooth covering with respect to L. And this, don't worry about the parameter. Epsilon, just think of it as 1%. So basically, how big does the volume have to be to get that? And what we show is that this is actually possible to achieve. And again, just with the random lattice, it's a nice thing. You just take a random lattice and you get that. So again, with Oded Regev and Barak Weiss, hopefully 23. So for all epsilon and some sigma bigger than 0, and for all convex K, bounded. And we show that the probability, and again, it's under random lattice chosen from this Dhar Ziegel nice distribution. The probability that you're kind of unlucky that this psi KL is the volume is or probability, let's say that you are lucky, that's less than n cube plus some epsilon, it goes to 1 with, and then it goes to infinity. So we have a more precise quantitative statement. I'm just simplifying a bit. Basically, what we're saying is that no matter what convex body you have, you take a random lattice, as the dimension goes to infinity, you expect that smooth covering density to be n cubed. So we had n squared when we talk about covering. This is a tiny bit worse. It's n cubed, but you get much more. You get actually smooth covering.
It's the same epsilon in the exponent. Seem to you're allowing yourself. It gets harder and harder in the exponent.
Simplify too much.
Maybe too.
It's probably not the same salary. Yeah. So it should be some sigma somewhere. Why would I write sigma? By exclusion, yeah. So something like that. Yeah, that's the right statement. Thank you. Yeah. So we have that statement. We also have a similar statement for other distributions of lattices, like if you know about construction A, or like more like discrete versions of random lattice, if you care about that. It's all basically boils down to the same proof, but let me focus on the statement. So again, take a random lattice, it's pretty good. It's not only good for covering, it's also good for smooth covering.
Oded, can you say something about this distribution of lattices?
I will say when I get to the proof, it has one very nice, it's a couple of very nice properties that I would use, yeah, to get some intuition. But typically those lattices, don't need to know it for here, but well, like the shortest vector is around square root n. They have many nice properties. I'll mention it a bit later, yeah. But it doesn't have to be exactly this one. The proof is sufficiently flexible. You can use versatile. You can use other distributions if you want. So nothing better was really known before for random lattice. So I think this is the first result, and I think there's hope of getting this. Well, you can ask Zev later, but I think there's hope of getting this down to n squared. I'm not sure. Actually meant to ask you. I'll ask later. So proof. So let's get to the proof, and there are 3 theorems. I'll mainly focus on the last one, theorem 3 on the smooth covering. But it's a similar idea in all of them. I can mention the differences when I get there. So what's the idea? Rogers was very smart. So why did Rogers do that already? I think one of the key observations we made here is basically connection to the finite field Kakeya problem. So all the proofs are basically by reduction to the discrete case, reduction to the case of finite fields, so FP to the n. And once we're there, we try to prove or use known Kakeya style theorems. Now, if you're experts in Kakeya, if you've seen statements of Kakeya theorems, it might not be obvious why this is Kakeya. I'll try to give you some intuition later why this is Kakeya, but Kakeya has many equivalent formulations and many parameters you can tune, and this is one of the incarnations of the Kakeya statement, and I'll try to show you why later. So the first paper was, we used all the work that came from the work of Zev. So this was the Dvir's 2009, the Dvir Koparty, Sarah Sudan 2013, and mostly the work of Koparty, Lev, Saraf, Sudan, 2011. We still had to improve a few things, so we had to prove a slightly stronger Kakeya-like theorem. That was for the first paper, where we had to prove just covering. For the more recent paper, we needed much more. I think we managed to get somewhere there. We managed to get some stronger Kakeya statements. But at some point, we had this brilliant idea of calling Zev. And 2 months later, we had exactly what we needed. So it was also simplifying many things for us. So this is how we prove theorem 3, which I describe now. So, but basically the idea again, is kind of you want to take your program, you want to reduce it to discrete question about Kakeya in the FP to the N. Let me say one thing, but something that was, I remember constantly worrying us when we did this, we were very worried that we're losing too much. Once we reduce things to a discrete case, we lose the convexity of the body. We have a question about arbitrary sets in some vector spaces over finite fields. And we were never sure if we maybe went, we were asking for too much because we start with something very nice, like some convex body. And typically it's been used in those proofs quite closely, quite heavily. And we decided not to do it. We just reduced to a problem about arbitrary sets in FP to the N. And luckily, luckily it works. So that's basically what I want to show you now. So luckily, even though you kind of lose a lot, you forget about the convexity, you're now in some arbitrary subset of FP to the N, you still have the same kind of Kakeya-like statements that you would like to have.
But you still use convexity.
I use convexity a lot, but at some point I just send it over to Zev and he takes it from there. And there, the Zev doesn't have to worry about convexity. That's kind of the matter. Of course, you need to use convexity a lot. So thanks, yeah, I didn't mean to apply that at all. So the first step is some kind of bootstrapping. We need to start somewhere. So we do some kind of what I would call rough packing and covering. So let me show show a picture so you see what I mean. So this is, I should have shown this before, just a lattice, and this is the fundamental cell. The volume of this parallelogram is the co-volume. I should have shown it before. So here's what we do in the first step. First step, we just take our body and just make it packing. Make sure that it it's a packing, so they don't intersect. So the first step is just to scale it down, make sure that it's packing. But we also want to make sure that if I scale it up again, like by a factor of 10, I cover all the space. So this is just bootstrapping. This is a very weak statement. It's been known for 50 years, kind of known 50 years that you can do it. Basically, I want to scale the body without lots of generality, so that it's packing like here. But if you imagine now scaling it up by a factor of 10, the radius now, yeah, exactly. The radius is scaled up by a factor of 10, which makes the volume 10 to the power n bigger, then everything is covered. Again, this is a very weak statement because the volumes are exponential. I'm aiming for volumes like n, n cube or n squared, but this is just to get space started. So the first thing I do is dilate K, my body. You think of Euclidean ball, but it could be anything such that the volume of K should be very small, maybe like 3 to the minus n. And then, again, this is kind of standard. Then with high probability over choice of L, again, we always take a random lattice, choice of L, two things hold. So first thing is that we know that KL is packing, like we were showing before. And this is where I start using properties of random lattices. This follows from, so basically the reason this follows is that what is packing? Packing means that if I were to increase the radius by a factor of 2, I don't touch any lattice point, right? This is basically what packing is all about, right? To be packing means that even if you go like distance 2 more, I will not touch any other lattice point. It will be this ball here, right? So to be packing just means that, and the reason this is true is because, again, you don't need to know the definition, but let me just briefly say it because this is nice to give some intuition, because the volume of 2K, if I scale it by a factor of 2, is 2 to the n, the volume of K, which is still much, much less than 1. And because of that, and then use Ziegel's summation formula. So Ziegel's summation. So you're asking me about what properties do we need of random lattices, and this is one of the main properties. It's called Ziegel's summation formula, and it says something very nice. It says this basically: if you have any set in space, and you're asking what's the expected number of points that a lattice has in that set. So take some ball, and you're asking, take a random lattice. How many lattice points are there in the ball? What Ziegel tells you, it's exactly, the expectation is exactly the volume of the ball. So we can very easily compute the expected number of lattice points inside any set, in particular in a convex set like here, like 2K. So because in particular, what we get is if you have a body like 2K and it's such small volume, a random lattice is going to miss it. Of course, there's an issue with the zero, with the origin. The origin is always there, but I'm ignoring the origin. So this is Ziegel's summation formula. And in fact, all the proofs of Rogers really use this and extensions of this. It's sometimes highly intricate, but there are extensions of this to compute moments of number of points in the ball. That's kind of how all the previous proofs work. So we know that K is packing, and I want the other direction. I also want to show that it's covering. So I want to show that if I just scale it up by 10, and again, it's a lot in terms of volume, it's like 10 to the n more. I want to show it's covering. Because this gives me like two. So I won't prove this part. We have a short proof in our paper, but it's those things are, this was kind of known. I mean, there are proofs, let me mention, there are proofs by Butler from, I think it was Roger's student from 72, and also by Bourgain. He did that in 87. I think he didn't know about Butler's proof.
It's a completely different distribution of lattices. So.
That's the thing. So they don't really work with random lattices. But if you look at Bourgain's proof, you could have done it. I think.
No, he does do a random lattice, but a much simpler model. It's a diagonal matrix, and then you put a.
Yeah, but converges in some sense to the same distribution. I think.
I don't think so.
Okay, in some sense it converges. But I think if you look at this proof, you can do the same proof, I believe, with this distribution.
Or maybe he has an advantage because he has a simpler.
Yeah. So it's a nicer proof, and I think the proof we have. It's different from his. It's also, I think, maybe even a bit simpler, I would say. But it is a very nice, Fourier theoretic, very nice proof. So again, the details don't really matter. Again, it's a very rough statement because the volume now, we're talking about bodies of volume 2 to the n. So it shouldn't surprise you that something so big covers space. I'm about to show you something like n cube, volume n cube covers space with a random lattice, not 2 to the n. So again, yeah, so they didn't exactly do that. I think for this statement, maybe it's really something we do in our paper, but yeah, it doesn't really matter.
For the random lattice, no, it's Margulis and Kleinbock, I think, have a paper that did it.
Okay, so maybe I should actually have the reference. I'll ask you later. I don't know the reference. But the Bourgain's proof is very nice. It's we have theoretic proof. And we have something similar. Okay. So again, why do I care about this so much? This is really why do I care about covering? And this is where it becomes more interesting. This is really the key to the whole proof is discretization. And let me maybe explain when you have covering, it means that any point in space is not too far from the lattice, right? You can move within this body of 10K and get back to the lattice. So it's covering tells you that you already have a good approximation of the continuous space with the lattice. So this is kind of intuitively what it's saying. I'll specify more precisely what I mean. So the next step is really the critical step. This is the kind of key of the proof. So let's take a big enough prime. I want to move to a discrete statement. So a big enough prime doesn't have to be very big. So P, maybe it has to be something like 10n or so, a little bit more, but something like 10n. So let's say like 10n. So it takes such a big prime and consider 1 over P times L. So basically, take our lattice, our random lattice, and shrink it by a factor of P. Okay, we get this fine grid. And if you think about this 1 over P L, right, this fine grid, if you take the quotient with L, you get something that's isomorphic to FP to the n. So this is where I get finally the discrete space. Let me show you a picture so it's clear what I'm talking about. Okay, so this is what I did. So I have those big points here. This is my original lattice L, right? There's those big points, and the small points are L over, in this case, 5. I took P equals 5 for simplicity. So you see the lattice, and I kind of shrink dilate everything by a factor of 5. So what this gives me is basically, if I think of this quotient, right, it gives me something like that. Right, so look at this like basic unit. It's like this basic parallelepiped or this fundamental domain, and you can see in there, if you just kind of zoom in there, you just get like f5 squared, right? You get like the 25 points inside this parallelepiped. Representatives of L inside 1 over PL. So this is really now. I mean, the whole question is really about like what's happening here, because everything is periodic, right? So if I understand what happens inside this parallelogram, I'm done, because just everything is happening periodically. So I can kind of zoom in on this one parallelogram and ask, what's happening in here. So specifically, what I care about is this. What I care about is, if I look at this body of mine, maybe it's the Euclidean ball, I care about what points are covered by the Euclidean ball. And I marked them here. And you can see this blue color, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So I have of these 25 points, right? I have 15 points covered by those balls. Okay, so again, I'm doing the same kind of question about covering, but all discretely. I'm asking in this discrete sense, how many points are covered by those balls? How many discrete points are covered by those balls? So again, I can zoom in and just everything can happen really here. Everything can happen within this basic repeated units. And the reason I can, and I'll show you later, the reason I can focus on this and not worry about other points, like what happens here and here and here and here, is because of that covering property, because everything is so close to this grid, close in the sense of K, of this convex bodies, that, if I know something about this discrete fine grid of space, I can extend it easily to all the points in space, to all of Rn. So that's why I need the covering of the convex body. So I know that basically I'm never too far from this discrete grid of space. So this is really all I have to worry about, what happens inside this FP to the n, inside this vector space. So basically what I'm doing is I'm saying let A be, so this is in FP to the n, just make sure. So A, FP to the n, the set of points covered, covered by K. So it's really just a discrete analog of that convex body of mine. Okay, just discretize everything, go to this final grid. And again, because the grid is so fine, I know that the fraction of points in A, if you look at this like finite field, the fraction of points, what should it be? Basically density of K, right? So the volume is very close to the volume of K. The lattice has co-volume 1, so it's just a volume, the density or just the volume of K. There's some to be precise, it's like within some some small fudge factor, like plus minus like 1 plus minus 10 over P or something to the power n. I mean, again, I'm not going to show the proof, but it's totally elementary. It's basically the idea is that any point in K you can associate to a point in the fine grid and you just do the volume calculation. But again, this heavily relies on that covering property that this body K covers reasonably well. So all I have to add basically is a tiny dilate, like 1 over P of K, and that doesn't really move things by much. So this is the first step. The first step, again, we have a fine grid. The details don't matter, but what you need to just remember, I have a very fine grid. So you expect the fraction of points covered by the ball to be its volume, just because the grid is fine enough. And fine enough turns out to mean we need that covering that we luckily have. Okay, now comes the heavy hammer, which is using Kakeya. So discrete smoothing, we call it. Basically, we want to have the same property we need about continuous space. We just want it for discrete space. So this goes back to your question, Avi. And we just defined notion of discrete smoothing. And let me show you what it is like. So we say that rank R subspace S. So I take some subspace of Fp to the n. We say that it's smoothest A if for all x in F p to the n, x plus s intersect with A. I'm going to demonstrate this in a minute, divided by p to the r. So the fraction of points in this coset of S that touch my discrete set A, that fraction should be kind of very close to its average, which is happens to be A over p to the n. So let me demonstrate this again with a picture there so you see what I'm talking about. So again, I have like F5 squared in this case, and I have the points in that dilated body K. I mean, high dimension is going to be very small. Here I happen to have 15 points out of 25, but high dimension is exponentially small. So now what I want to find is this kind of smoothing subspace. So let me take a subspace here, like the subspace maybe here, those 5 points in subspace. That's not a good smoothing subspace because the subspace has now 5 points in A and it's coset here. So this is 5, this is 1, this is 4, this is 1, this is 1, and this is 4. So that's not a good smoothing subspace, too many fluctuations, 5, 4, 1, 1, 4. What I should do instead, take a different subspace, like, let's take, like, well, it's hard to draw, but like this. And then you see I have exactly 3 points out of 5 points. And that would be true even if I now shifted this. And let me show the, if you don't believe me. So this is the squares indicate the S, the subspace S. You have 1, 2, 3 blue points in the subspace. And the nice thing is it's not just a subspace, but also if you shift, like you take cosets of the subspace, you again get here. You again get 3 points. This is really perfectly smooth. It's exactly 3 points. Here I get 3 points. Here I get again 3 points. And here again, I get 3 points. Okay, this is extreme. Everything is exactly the same fraction. Everything contains exactly 60% of the subspace. So the question is, how do we actually find such a smoothing subspace? Do they even exist? And that turns out to be very much Kakeya-like problem. So it doesn't maybe immediately feel like that. If you think of Kakeya like a set containing a line in any direction, I can explain how you get there maybe later. But trust me that some evolution of Kakeya gets you to a statement like the following. So for the first paper, we proved something else, but this is the strongest. This is the statement we need for the latest paper. This is Manik Dhar and Zev Dvir proved last year. And basically show the following amazing things, that if you have any subset of Fp to the n, it doesn't have to be any convex or anything like that, whatever convex would mean. And if you have some parameter r, that's the rank, okay, r, such that, so I want to make sure that the rank is not too low. So I want to make sure that the cardinality of A times p to the r is at least p to the n plus 3. And this 3 is the same 3 we have. Okay, this 3 is the same 3 we have in our statement. It says that if you just take a random rank R subspace S in Fp to the n, it's smoothest A. Smoothest A with high probability. Smoothest A with high probability, assuming that P is not too small, provided P should be a little bit bigger than N. Okay. So let me just explain one thing. So basically they're saying you take an arbitrary subset of Fp to the n, take a random subset, a random subspace S. The condition here is actually quite natural. Let me just show you why. Without this 3, if I remove the 3, what this would be telling me is that, so what's shown here is that the average number of points per subspace, that I have in a subspace. If I remove the 3 here, I will end up with situation where I have on average either less than 1 point per subspace. Basically, this is why I need this extra cushion. So, and I think you probably need 1 here at least. I don't know if you have any better sense of what's the tightest you can get, but you can definitely not remove the 3 altogether, because at some point you just get less than 1 point on average in each subspace, each coset, and then of course it's not smooth because sometimes 0, sometimes 1, sometimes 0, sometimes 1. So you clearly need some, something like some law of large numbers or something to help you. So this clearly cannot be avoided. Something here, some condition like that. I'm not sure about the 3, whether the 3 is like it.
It has to be at least 2, I think.
At least 2?
Because I mean, this term is only true for R, which is at least 3. This is what we proved. It's implied by that inequality, right? That R is at least 3. Right? So for R equals 1, it's not true. So it might be true for R equals 2.
Yeah, okay, but I'm willing to take R big, but I want to still improve that relation from Some is okay. Well, let's see what you see. Okay, so I think at this point, if you believe this statement, at this point we're essentially done. It's not maybe totally obvious. Let me just mention why we're done. If you think of what this is really telling you, the smoothing I was showing you before, saying that all cosets of S touch A in the same number of times is the same as saying that if I were to move A by this coset by S itself, that's the kind of number of times that it hits X. I'm basically subtracting, from both sides, subtract S or something. So it's counting the number of times shifts of S are above X. So what this is saying is really this theorem telling me that if I take a random subspace and then densify my lattice, which is step number 4, densify is telling me that I'll get good smooth covering of the discrete space. So let me show it in pictures. So we have this good subspace, and what we do with it is basically this. We take our lattice L, this is our lattice L, and we kind of densify it. We add those 4 points, so make it 5 times as dense, okay? And at this point, I claim, after we do that, so I take those points here, and that's what it looks like. I'm making it 5 times as dense. I'm adding those points coming from the subspace that the Kakeya statement gives me. And this point, it looks something like that. Okay, so what is that? This is the slightly densified lattice by a factor of 5 in this case. Generally, it's a factor of P to the R. And it has this nice property, which you can kind of see here, that any point at least in the discrete set, is containing exactly 3 balls. So any point will be containing exactly 3 balls. So no matter what point I take, it will be in exactly 3 balls. So this is exactly what, or in this case, it's exactly 3, but generally it will be within like 1% of the average. So to summarize, at this point, you just define the densified lattice. So define L of S, let's call it L of S. So it's something like that. I'm basically adding the subspace to the lattice. So maybe I write something like that. It's not the best notation, but it's somewhere sitting between the grid and L itself. And then we're done. So while we're done, you have to notice a few things. So the first thing is that K and S, so within lattice, the same set K, the same body K is a smooth cover of the discrete set. And this is really the Kakeya statement. So it's a discrete, it's a smooth cover of L over P, of the whole discrete grid. And I was telling you that this is basically saying that you can extend to the whole space because the grid is so fine. You have to show this. This uses again the covering property, this rough covering, but this also implies is a smooth cover of all of Rn. Smooth cover of all of Rn. So this is great. We get a smooth cover. How good is it? So 2 more things I have to say. Yes.
L of S is not a random lattice.
That's the next point. And that's another kind of remarkable thing about the distribution. Since L is a random lattice and S is a random subspace, Yeah, you have this property that L of S is also that up to scaling. It's a bit denser at P to the R, but up to scaling it's still the same distribution. And the reason why is actually not hard to prove. It's invariant under linear transformation. So you can show it has this property. This has a name.
Different linear transformation. This is over FP and this is over the
You have to make sure it's sort of things commute in the right way. But this is okay, I believe. And this is called by the name. It's called a Hecke correspondence. So it's not that we invented this transformation. You don't have to know the name. So yeah, so we have almost everything we need. We have smooth covering of space. We know it's a random lattice. We just have to calculate how dense the covering is. And this is so the covering density is. So we have a lattice of co-volume P to the negative R because we densify things by a factor of P to the R when we add that subspace. And we just have to multiply by the volume of K. And if you do the calculations, so this is roughly P to the R times A over P to the N. I told you that the volume of K is roughly like the density of A in this vector space. And this is roughly P cubed. And this is roughly N cubed because P is roughly N. And that's it. And I'm out of time. Okay. Thank you.
Thanks. Any questions?
Can you maybe say one sentence why this version of Kakeya, how it's related to the more usual?
Right, what's the connection? Where is Kakeya? So,
Yeah.
Because usually when you think of Kakeya, you're saying, I want some set in FP to the N, such that, any direction I take, one of these lines will be contained inside the set, okay? So this is, let's call this set like B, this set that is Kakeya set. And Kakeya says that if you have such a set that contains each direction a line, it has to be big. Because, you can't do it with small sets.
Yeah.
Now you can ask different version of Kakeya. Maybe I don't want a line in all directions, maybe only like 1% of directions. So 1% of all random directions, 1% of them, I should have some line in this direction. There's a way to find a line in this direction. So this is a variant of Kakeya. This is what we proved in that earlier paper. So it's a Kakeya with 1% of directions. So what's the connection? The confusing thing that you have to do is that you want to work with the set A, that's the complement of B. That's the confusing logic here. You want to think what Kakeya says about the complement of the Kakeya set. In that language, it tells you that in 1% of directions, right? Sorry, I managed to get myself confused. So Kakeya says in 1% of directions, you get a line, which means that in 99% of directions, no matter where you go, you don't have a line, meaning that you cover. If the line goes, it touches the set. So in 99% of directions, and let's get the logic of 99% of directions, if you look at the direction, everywhere you go, you always touch the set. So if you project, you get full projection, you get the whole. And so this is actually what we did in the first paper, which is just covering. I want to make sure I at least touch the set once. What the new statement does is not only once, but you have to touch it in the right number of times. You intersect the set in the right number of times. But this is a kind of more for historical, like how to connect this to the historical statement. I think in the recent paper, you really directly express it in terms of hashing, in terms of L infinity hashing.
I think of it as just what happens when you project in a random direction. It's the same, but you need at least 3 dimensions. It's not true for lines. So for lines, there are counterexamples. There's small sets that behave weird, but for dimensions 2 and 3, we don't have we don't have any interesting.
But you also know there is a qualitative difference, right? As you go from 1 to 2, right?
Yes. From 1 to 2.
That's much stronger bounds.
For 1, the thing you need is not true.
Yeah.
And for 2, it's true for exponentially large fields, and for 3, it's true for polynomially large fields.
But notice we don't really care about R being 1, 2, or 3. I mean, we really care about the gap and how much you lose from the optimal hashing, right? So
you need P to be N and not N squared.
Yeah, because we currently lose P cubed, so P should be very close to N.
The covering effect.
Yeah, I just wonder whether you care a little bit about what R, and you cannot take R equals M.
So R really has to be, if R has to be very close to as small as possible. So this is, if you look at this here, you can write that R should be something like, so if I just solve this, is n plus 3 minus log base P of A. And the smallest it can imaginably, like if you were very naive, you would say it has to be n minus log P of A, because you have to, on average, expect to have at least one point of intersection with the discrete.
It's not that any hour.
Yeah. So I really want it to be as close as possible. So, it would be nice if 3 could be 2. And it's okay if you have some bound that R has to be at least 10. It's okay, but it has to be as close as possible to this.
So two quick questions. One, I didn't quite understand how the covering property of 10 times k was used. Is this statement true for any, like for a little ball, big ball statement? If I have an arbitrary set that's small and an arbitrary set that's big, but this set is sort of almost invariant under the small set, would you get the same result, or do you need to know that it's actually convex and actually 10 times k or something?
When you use the n that P was, you replace P by n. If P was n squared, it would probably get n to the
to compare the continuous volume, the discrete volume. That's where this big covering thing is needed.
Yes, I use it. Let me find it. I use it in a couple of places. It's all over the place, like things like that. Like, it should be a good like discretizer. So, and the way I actually prove it is you're saying, think of all the points that in the discrete set, you can put like a little ball around them, and that little ball needs to be just enough to make sure you can cover space. So, so you can do this covering volume argument. So, little ball would have to be something like 10 over p times k. Because everything is scaled down by p. I take a fine grid, like it's n over p, and I know that 10k is covering for L. So 10 over pk is covering for L over p, for that very fine grid. The nice thing is that if you think about this 10 over pk, if you think of like if I add it to a ball, so the ball becomes a tiny bit bigger, but it's almost invisible in terms of volume, because it's crucial. It's something like 1 over n. But once I add like 1 plus 1 over n to the radius, almost no effect on the volume. But that's why I want to make sure like I can do things like that. So I use it in a couple of places.
Just to amplify Freddie's point, it might be possible that these results hold not just for convex bodies, but maybe for approximate groups, or some larger class of objects that, for example, arithmetic progressions of convex bodies. Things are good additive structure.
Where you sort of extract out the property that you need of these convex bodies, and it's much less than being convex, right? It's sort of, you just need, at a couple of good scales, you need some good behavior or something. Sorry, I just want to ask one other thing very quickly. So you don't actually have to work with FP to the n. You could work with FP to the anything less than n, right? Because you could use a cyclic sublattice or something rather than just dilating by p. Is that just the wrong way to go?
Well, interesting. You can imagine like a different supergroup. We don't have to go to L over P. You can take some other, could be, if you can guarantee somehow. Yeah, I mean, sometimes the bootstrapping is very rough. You're right. I mean, I start with some very rough bounds, and I don't think it could be. Could be that you can sandwich it a bit closer, and then I don't need such a strong Kakeya statement. It could be. It's very loose, but yeah, some of my feeling is that it doesn't really, we don't pay much for it, even though it's so loose. We don't have to pay so much for this.
Kakeya technology is very good, and so a large n is not the problem. You have to do the end statement or something, except if you're lazy and you don't want
it's kind of, we offload almost everything to Kakeya. This was not the case in the first paper, and generally, I mean, we always struggled with exactly like kind of questions like I want the body to be as close as possible to covering just like the last mile, but by this point the Kakeya is so strong that we don't have to do anything. We start from very naive bounds, very rough bounds, and covering Kakeya takes us the whole way there.
One place like where the Kakeya technology is really bad is distinguishing between fields with subfields and without. So you need this for FP. And what we do is for any field. And when we have subfields, there are weird constructions where you have a lot of lines with many points. And so this is one thing where we really are stuck, is using the, let's say, probably stronger things for prime fields, which might be useful.
I see, because the statement I didn't say, I should have said the statement is true for any prime power finite fields.
So, right, this is discretization, reminds me of Einstein's work on a distribution for lattices, which is for these problems are ever space hard and all this quantum cryptography stuff. So his distribution is a distribution over lattices, which is built from finite fields. I assume your proof would work for this distribution, maybe even easier.
So that's really,
that's a guess.
that's absolutely true, actually. So two things. First, that's really where partly the motivation comes from. I should have said
I should
that.
have asked you, I remember you when you were a postdoc.
Like the smoothing. So we, in cryptography, often need that. To be honest, usually, not always, but usually you don't really care about this everywhere smooth. It's okay if it's smooth in some N2 sense. And then it's really very easy to prove everything here. So, but there are cases where you could benefit from L infinity smoothing. So it's potentially useful in cryptography. And I-tie lattices are, I think it's basically what's known as construction A lattices. And yeah, this proof, because we don't really use that much about the random lattice. You could do it with that. And that's also how we write in the paper. You can do it with, like you take it's basically in a random subspace of FP to the N.
And then so a follow-up with my measure to that. I mean, so it's a distribution with much less randomness. Do you know or imagine an explicit construction of a lattice that has this property? That has such a smooth covering.
Not just packing. I mean, just getting. I think just for packing, I'm not sure what's known in terms of that. Like, this is a maybe more classical question, but it could be easier here.
Covering almost always easier in almost all contexts here. So you don't need for an explicit.
I don't, like you say, you reduce the randomness. What's the most explicit construction of a good covering? Say for Euclidean board.
I mean, do you have any idea how one would look like? Some properties of this matrix.
But you believe the Bourgain's example distribution works. That's the diagonal matrix, and then you do just one random vector in the last column. Or each entry independent with 0, 1. That's all he did.
Yeah, so it's basically.
And then you read this as an and with that.
But it's the same. It's really random matrix.
It's n bits. Or minus 1.
Well, the accuracy really matters. You need many bits of. I think it's n squared if I look at it. It's like a matrix.
Yeah, but forget no one. That's explicit construction. What a lattice like this look like.
But this is actually n log n bits because it's fp to the n and p is like n. So this is maybe slightly better in that sense. Yeah, I don't know. More questions?
Okay,
Thanks.
Thank you, Megan.